Okay, hello, I'm Sudeep Kamath. I'd like to thank the organizers for inviting me. I'll talk today about learning distributions from samples, and the setting is a minimax risk formulation. Okay, so let me begin. This is joint work with Alon Orlitsky, Dheeraj Pichapati, and Ananda Tirtha Suresh. Okay, so here is the setting. Consider the problem of learning probability distributions. N samples are drawn IID from a fixed distribution on an alphabet of size k. So x1 through xn are drawn IID, and this distribution is a distribution over a finite alphabet. K is known to you. Keep in mind, n is the number of samples, k is the size of the alphabet. And the probability distribution takes values in the k simplex, which I'll denote by delta k. Okay, so to formalize our problem, we need a loss function, which is a numerical penalty for estimating the true distribution p by your guess q. So this is a number which measures how bad it is to guess the true distribution p by q. So throughout this talk, p is going to be the distribution which generates the samples, and q is going to be our guess. Our guess is based on the samples. The distribution is unknown to us. Okay. The minimax risk formulation is the following. For every possible probability distribution p and every estimator q, which is designed based on the samples, you incur an expected loss. The expectation is over the randomness that the samples are drawn according to p. You maximize this expected loss over all distributions in the simplex and find the estimator that minimizes this worst case loss. So this number, RKN, R stands for risk, K is the alphabet size, and N is the number of samples. Just tells you that this is really the best you can do. If you choose this estimator, no matter what is the underlying true distribution, you will not incur a penalty more than RKN. Okay, and the question is, what is the minimax risk and what is the optimal estimator? Give me a characterization of RKN and the best estimator. And of course, the answer will depend on what is the true loss function being used. So finding the exact answers to these questions is often difficult. And in this talk, we will look at asymptotic behavior of the minimax risk as the alphabet is held fixed and number of samples grows large. Okay, here are some important measures of loss functions that are used in practice. Relative entropy, or the Kullback-Leibler divergence, scale divergence, important in compression and prediction. There is the chi-squared distance notion of loss, important in multiple correspondence analysis. There's L1 distance, very important in classification and machine learning. And there is Hellinger distance. I'm just giving you some examples. All of these notions of distance that I'm talking about here are actually special cases of the F divergence by Chizar. For any convex function f, where f of 1 is 0, you can define a notion of distance between p and q given by this formula. And all the ones I just talked about so far are actually special cases of the F divergence, although there are other notions of distance as well. Okay, here is the outline of the talk. I will give you two stories related to these notions of distance. One, the minimax risk for relative entropy. This is an old story, so it's more of a literature review. And then I'll give you some of our new results on chi-squared distance. We have some other results as well on L1 distance and other distances, but I'll not be talking about it today. So I'll talk about two stories, the relative entropy first and then the chi-squared distance. Okay, so relative entropy, let's look at this. We want to find the best estimator which minimizes the worst case expected loss in the relative entropy sense. Okay, the first thing, very obvious thing you'll notice is that empirical estimator is a terrible idea, because if a symbol has a positive probability of showing up, but for some reason, with low chance it never showed up in your samples, and you assign it a 0 probability, you will incur an infinite cost. So you would not be using the empirical estimator. And in fact, any estimator you use must satisfy Cromwell's rule that you should not assign 0 probability to any symbol. Cromwell was not a statistician, he was a military leader, and he used these words to the Church of Scotland. And in subjective probability, one says that if you assign 0 probability to an event, you're not allowed to change your mind by Bayesian updates. And so that's what the rule means. But in our context, we will not be assigning 0 probability because we don't want to incur an infinite cost. Okay, so what else could we do? Here is a very famous estimator, the Laplace estimator. This was Laplace's answer to the sunrise problem. The probability you assign to a symbol is proportional not to the number of occurrences, that would be the empirical estimator, but to the number of occurrences plus 1. So therefore, if you see the sun rising for n days in a row and the sun has not risen for 0 days, then Laplace would assign a probability to the sun rising tomorrow by this formula, n plus 1 over n plus 2. This was Laplace's famous answer to the sunrise problem. A more general family of estimators is the add beta estimator. Here the probability you assign to a symbol is proportional to the number of occurrences of the symbol plus some constant beta, which is positive. And Laplace is a special case where beta is equal to 1. Okay, here I tie in with the previous talk. There's some very good news associated with this family of estimators, and that's the following. This is a related problem. It's not the same problem. It's a different problem, but it's closely related. We don't want to minimize the expected loss at time n, but we want to minimize the running sum of the expected losses from time 0 through n. So at each time you come up with some estimate based on the samples you've seen so far, and the loss you suffer is the sum of the losses from time 0 through time n. So this problem becomes the minimax redundancy problem in universal source coding that Stefan talked about. And for this problem, it's very well known, very famous result, that add 1/2 is asymptotically optimal. So the add beta estimator with beta equals 1/2. It's been known for a long time, more than 30 years. And the asymptotic behavior of this quantity is nailed down to constants by work by Wojtek and Marcelo Weinberger and others. So this quantity is, perhaps you might think that this is a more complex quantity than this one, but it's very well understood. Okay. Now, what does that mean for our quantity, where we want to minimize only the expected loss at time n? Here there is bad news. Krzyzewski showed, firstly, that if you want to use add beta, beta equals 1/2 is not the best beta. And furthermore, there is a natural lower bound on RKn. K is the alphabet size, n is the number of samples. We are looking at loss under relative entropy distance. There's a natural lower bound, k minus 1 over 2n. And the best possible add beta rule is off by a constant factor. You cannot achieve that natural lower bound. Okay. And after a series of papers on this particular problem, this was completely solved by Brace and Sawyer, the asymptotic behavior. So which of these bounds is really the correct one was discovered only 10 years ago. Brace and Sawyer. If you're wondering, it's indeed the same Brace from Brace paradox in traffic flow. The answer is the following. Sorry?
Which Sawyer is it?
Yeah, Tom Sawyer. He's really Tom Sawyer. Wait a minute. I hope I'm not wrong. I believe it is Thomas Sawyer.
That's Tom Sawyer.
The lower bound is tight. That's the answer. Okay. The lower bound, the asymptotic behavior, the first order term is k minus 1 over 2n. But of course, no add beta estimator would achieve this. That already Krzyzewski showed us that. So in fact, the optimal estimator, which achieves the first order term, was described by Brace and Sawyer to be the following. It's a varying add beta rule. So the probability you assign to a symbol is proportional to the number of occurrences of that symbol plus a beta that also depends on the number of occurrences. Okay, if you see a symbol I times, the probability you assign to it is proportional to I plus beta I, and beta I is given by this formula. Beta 0 is 1/2, beta 1 is 1, and all subsequent betas are 3/4. This is an estimator which gets you this behavior. So it seems somewhat strange, and I'll remark later why this kind of thing is happening when I talk about chi-squared distance. So let me move to the chi-squared distance story. Here we want to minimize this particular form of loss. Okay, the chi-squared distance between P and Q is given by this sum. The best choice of Q here is Pi itself, in which case the loss is 0. And in every other case, it's strictly positive. You want to minimize this. Again, Cromwell's rule applies. You should never be saying Qi is 0, no matter what you see. And because you would incur an infinite cost with some probability. So you should not be using this estimator. And here is our main result. for the chi-squared distance notion of loss, we have a non-asymptotic upper bound and a non-asymptotic lower bound on the minimax risk. So for every possible size of the alphabet k, and for every number of samples n, this is an upper bound on the minimax risk, and this is a lower bound. But still these bounds are pretty sharp. For example, if you fix k and make n very large, then these bounds tell you that the first order term in the behavior of the minimax risk is precisely k minus 1 over n, up to, and in fact k minus 1 is exactly the right constant here, and that the second order term is at most logarithmic log n over n squared. Okay, if I had more time, I would have liked to go into more details of this proof, but I would not be going into the details today. Any guesses for what is the estimator that achieves this upper bound? A wild guess? Sorry? No. A very simple estimator does, and it's the Laplace estimator. So the add one rule gives you a performance that's at least k minus 1 over n plus 1. Yeah, I'll come to that question. That's a good one. So I've chosen to skip the details of the proof because there is something, I mean, not in the proof of this result, but there is something strange going on here. Black magic. Something I find really very weird and very surprising, and I want to go into the details of what is that thing that I find very strange here. Okay? To describe that thing to you, I want to fix the alphabet size to be binary. Okay, even with binary, you should be able to appreciate it. So k equals 2. Alphabet size is 2. So now the probability distributions are basically parameterized by one number, p. P is the probability that x takes the value 1. 1 minus p is the probability that it takes the value 2. And so the expected loss under a Laplace estimator is this thing. Let's parse this expression. The thing in brackets here is the chi-squared loss function. The thing in green is precisely the Laplace estimator. If you see I occurrences of a symbol 1, you assign it a probability that's I plus 1 over n plus 2. And the thing in red is the probability that you will indeed see I occurrences of the symbol 1. This is the Laplace, this is the expected loss under the Laplace estimator. And it's a very simple calculation to show that this is 1 over n, upper bounded by 1 over n for every single value of the parameter p. And that gives you really the upper bound that I talked about. It's a trivial calculation. But really the surprise and the weirdness starts with this question in the spirit of XKCD. What if you chose some other estimator? We'd use an add beta estimator instead. And that is the question I want to ask. So instead of beta equals 1, let's say you started out with some other beta and tried to prove the same thing. What would have happened? So here is the loss now. Let's look at this expression again. The estimate of probability of a symbol that appears I times in the sequence is I plus beta over n plus 2 beta, because we are using an add beta rule. Okay. Let's recap. There's so much things going on. N is the number of samples we're drawing. P is the one parameter that characterizes the probability distribution on a binary alphabet. It's the probability that x equals 1. And beta is basically the add beta estimator. Okay. If I see a symbol occurring I times, I assign it a probability that's this. Okay. And this thing here is the expected loss you see when you use the add beta estimator. Let's give it a name. I'll call it f of p with n and beta as parameters. Let's see a plot of this function. I've taken 10 samples. I've drew 10 samples. And on the x-axis is the parameter p. The y-axis is the expected loss at the parameter p. And I've chosen 3 different values of beta. 1/2, 1, and 3/2. Beta equals 1 is my estimator, Laplace estimator. Okay, and it's good. All these losses are very small. They're of the order of 1 over n, 0.1. Now if I increase n, suppose I make n very large, what do you expect will happen to these curves? You're getting more and more information about the true parameter, so you expect that the loss should go down. So let me take n equals 100 and see what happens. So all these curves are actually very close to 0. That's nice. And in fact, you can imagine these are all polynomials in P. This is a polynomial. I've drawn for you 3 polynomials of degree 102. Okay, but because we can't see them properly here, let me scale up the y-axis to be able to see what's going on really. And here is the scaling. The right scaling is to look at 1 over n. I draw a black straight line at 1 over n because that's where I expect the answer to be, right? And then here are these 3 curves. There's a green, blue, and red curve. Green corresponds to beta equals half. Blue is beta equals 1. Red is beta equals 3 by 2. All right, what do we see here? Look at these curves. In the middle, they're pretty much constant. And something strange is going on both the endpoints. Okay? So to see what's going on, I'll zoom into the endpoints now. So instead of looking at P from 0 through 1, I will make the x-axis also have units of 1 over n. And this is what it looks like. So just to summarize, two slides ago I showed you what it looks like n equals 100. And then I'm just looking at this corner using a microscope, using a magnifying glass. This is what it looks like. Both dimensions are now of order 1 over n, and I see these curves. You see, of these 3 curves, the green, blue, and red, only one of them is always below the straight line 1 over n, and that's the blue curve. That's beta equals 1. That's the Laplace estimator. Beta equals half starts out below the curve, but then goes above, and then starts coming down. Somewhat strange. And beta equals 3 by 2 is also starts out above the line. So you might think this is a function of n being 100, which is probably a small number. If n becomes very large, maybe this kind of thing will go away. So let me take the limit of this curve. Let me keep zooming in and make n larger and larger. N goes to infinity. This phenomenon remains. So at the boundary, for very tiny probabilities, the expected loss is above 1 over n, no matter I choose beta equals half or 3 by 2. And in fact, it turns out to be the case that if I draw a curve for each beta, only one of these curves is always below the line 1 over n. So if I take the maximum of the expected loss over the entire range, I will incur a loss that's c of beta over n, and c of beta, strangely, is equal to 1 only for the Laplace estimator. For any other estimator, you are off by a fixed constant factor. This is the thing I wanted to really talk about. And what this says is something, there is a tremendous amount of serendipity involved here in finding that the Laplace estimator actually matched the natural lower bound. And so if I tell you 2 stories, one for relative entropy and one for chi-squared distance, how many other divergences or how many notions of distance would you want to understand the minimax risk for? Well, for relative entropy, I told you this is optimal, okay? This strange looking thing is optimal. Now you can imagine why. Because at the end point, strange things happen, and you need to perturb the estimator in sharp ways so that it lies below what you want. For chi-square distance, something beautiful, Laplace estimator is asymptotically optimal. Add one works. Why is it so much simpler? What is it in chi-square distance that's not there in relative entropy? Then it becomes so much simpler here. And the short answer to this question, which I also believe is accurate, is luck. It's just, it's something I do not fully understand. The expected loss near the boundaries of the simplex depends very erratically on the loss function you choose, relative entropy or chi-square distance, and on the specific estimator you choose. So there's some strange thing happening on the boundaries, and if you want to have a coherent understanding for various notions of loss, for example, a family of f divergence loss functions, seems to me highly challenging because of this specific thing happening on the boundaries. For example, if you look at Hellinger loss, same thing happens as in relative entropy. The best add beta estimator cannot match the performance of the natural lower bound. So you might have to look at strange estimators like this. So if the boundaries of the simplex are causing these problems, one thing you could do is avoid the simplex boundaries. And now look at a very general notion of loss. Let's look at f divergence loss. And here is our result. Suppose the probabilities are bounded below by some constant alpha. Okay, all the PIs are required to be larger than some number alpha, which is positive. Let f is going to define an f divergence. It has to be convex. F of 1 is 0. What Ramon would call mild assumptions. f is thrice differentiable and sub-exponential. And truly they are mild. I'll come to why. In this case, the minimax risk depends on alpha, of course, the parameter that bounds all the probabilities from below. Two differences here. The max is now over all these probabilities that cannot be very close to the simplex boundaries. And the loss is an arbitrary f divergence loss, where f is this function. This has a very simple formula in terms of the function f. It's k minus 1 times the second derivative of f at 1 over 2n. So this unifies all these existing results under this constraint.
Why doesn't alpha show up in this formula?
Yeah, that's a very good question. Alpha does not affect the first order term, it turns out. And what is the estimator that achieves this? Any add beta rule for any beta positive is asymptotically optimal and gets you this. So if you want an intuition for this result, look back at that picture I showed you. There are three different betas here. All of them between 0.2 and 0.8 have about the same performance. It's only at the boundaries that there is some erratic behavior happening. And why are these assumptions mild? Well, because you can choose various other notions of losses which are not even f divergences. Any smooth function which is quadratic for PQ being close satisfies an essential result of this form, as long as you avoid the probabilities that are very, very close to the boundaries of the simplex. So that's really all I have. In summary, I described to you the minimax risk. Minimax risk for a general loss function. I gave you non-asymptotic upper and lower bounds for chi-squared notion of loss. And these bounds were quite sharp in that they characterize the first order term in the asymptotic behavior when the alphabet size k is held fixed and the number of samples n grows. I suggested that a general formula for a wide family of loss functions, such as an arbitrary f divergence, seems to be a difficult prospect. And that's because of the erratic behavior at the boundaries of the simplex. So if you avoid the boundaries, then any add beta estimator is optimal. And there's this very simple formula for the minimax risk in terms of the loss function. We have all these results and some more on other notions of distance, L1 distance and other distances coming up on arXiv soon. Thank you very much. Yeah.
So your estimator is actually Bernoulli sum what you're estimating. And this is quite well understood. You can get any asymptotic that you want for fixed p. Your problem is that you want uniform asymptotics.
For all p.
Non-asymptotic exactly work. Uniform asymptotic, Sahi and his team knows how to do actually for uniform asymptotic for all p. I think you have to talk to them. Because they are dealing with this right now.
Okay. Max?
So you probably know this result that any f divergence can be expressed as an integral with respect to a suitable measure of base risk divergences.
Yeah.
Have you actually looked at just what happens with the base risk divergence?
No, I have not. Perhaps you can understand base risk even including this erratic behavior.
Right.
But our loss function, we have made some assumptions here that f should be smooth and so on.
Sure, yeah. But the point is that any f divergence can be expressed as an integral of base risk.
But we don't expect this behavior to be, for example, 1 over n, because even for the total variation distance, we have a 1 over square.
So I think it would depend on that measure that averages the
Yeah.
prior parameters. In the case.
Yeah, that should be smooth or something.
Right, yeah.
Thank you. Saki?
Is there any relation between this k minus 1 over n factor that you have throughout your results, and also in the context of growth of entropy, and the same k minus 1 over 2 factor that appears in the minimax redundancy?
Yeah, that's a very good question. The two notions, the minimax risk and the minimax redundancy, are related. K minus 1 shows up because it's the dimension of the simplex, the number of free parameters. And this number gives you, if you can characterize this number, it gives you an upper bound on the minimax redundancy. And Brace and Sawyer showed that upper bound is nearly tight because this behaves like k minus 1 over 2n. And when you add this up over n, you get k minus 1 over 2 log n. But it need not have been tight. It happens to be the case that, in fact, you get exactly the right constant also.
First of all, so
for this kind of result, you are taking n equal to infinity, but k is fixed. So here is a little o term. Can you characterize what's the hidden k in the little o term, but not only n? So for example, for them, I like n and k go to infinity together. What's the asymptotic? What's the rate? Second thing, actually, recently we have improved the result in Brass and Sauer. And in their result, they are doing roughly similar thing as you did. You scale it back and roughly look at the C beta, so you get this little bit jump. But actually, we characterize the non-asymptotic performance, give very tight upper and lower bounds, and which improves over that.
That's a good comment. Yeah, there is some dependence here on k as well as alpha. And if you make k and n both scale in some way, then I do not anticipate that a simple formula like this might be available. But for chi-squared divergence, we have non-asymptotic bounds, and they give you the correct scaling even when k and n grow together. Thank you. Varun?
So I was just thinking, if k is going to infinity and your alpha is sort of remaining fixed, you're sort of shrinking the simplex from its original size to be away from the edges. And for large k, it's essentially zero volume inside, like you're missing out all the...
Oh, yeah, you're right. So in this result, I'm going to actually fix alpha, but k is also fixed. If I fix alpha and then make k go to infinity, then this doesn't make sense, because there are no probability distributions satisfying this. Yeah.
So in this result with the alpha assumption, you're in some sense eliminating the rare symbols. And every symbol that appears many times. You're sort of in the regime with the law of large numbers is working for you. So is there some intuition for why you can't choose beta equals 0?
Yeah, that's really great question. I want, if I had more time, I would have elaborated on this result. These assumptions are really mild. The only reason I put a beta positive here is because the F divergence may give me an infinite penalty at some points, like for example relative entropy. So you're right. Suppose I want to use the empirical estimator. There are a wide family of estimators that will work here. This add beta is only, the sub-exponential assumption is only so that add beta works. Remove the sub-exponential, remove add beta, use the empirical estimator, except if your empirical distribution assigns 0 near the endpoints, then just say uniform. That estimator will give you this performance.
So the lower bound for chi-square probably is coming from using a prior, and is it add 1 square, is the beta 1 1
Yeah, the lower bound I described to you comes from evaluating the base risk under the uniform prior.
So then, can we say something about the beta 1 1 prior is minimax, is the least favorable prior, sir?
Yeah, I'm not very sure about that. I don't know. I don't know if the least favorable prior is to choose uniform. And if you scale the alphabets in some way, I suspect it's not.
Well, yeah, if there's time. So in the regret regime where you sum the loss over rounds, we have the notion of Vogt mixability, which allows us to relate other losses to the log loss, and you get a lot of reductions that way. I'm wondering if there is a similar thing going on here, because the two losses you mentioned are exactly kind of the two famous mixable losses. So could that be the reason why these things look so similar?
So then we have another result which I did not describe. You can consider the minimax expected sum of losses from times I equals 0 through n, and we can show that as long as the PIs are bounded away, the expected loss behaves like k minus 1 f double prime over 2 times log n. I don't know how it's related to the mixability problem. But this is easily extended to the case where the loss is not at time n, but at time running from 0 through n.
Since the lights went out, so